Start recording. Okay. So there we are. Like on Monday or Wednesday? Sure. I think I could probably bring you guys pizza. Will you guys come on Monday if I bring pizza? What kind of pizza do you like? Cheese, pepperoni. Are there any like vegetarian or vegan? Is any? There's probably are, right? Okay, if you're in class today and there are dietary restrictions regarding pizza, email me and then I'll try to bring pizza on Monday for everyone. So yeah, we'll have like a little review party with food. Oh, you don't have to. I mean, like it's oh yeah. We also need drinks, I guess. All right, I'll give that a try. That is a good idea. Okay. Anyway, let's get started, guys. We have this is our last real lecture, so let's cover some good stuff. So reminder again, final exam is going to be on Wednesday. I have the practice final ready to be released today. If you guys could look at it over the weekend and come with questions on Monday, that would be great. Otherwise, it's fine. I'm probably going to go over it on Monday and Wednesday and like talk through the different topics for the practice final. Okay. Oh, I did not update this. I think our progress is probably higher. I didn't update this from last lecture. I think this one's almost at 80% probably. I think Chi told me we're like at 51 or something. I think this one we're like at 30% or something like that. So I don't know what's up with. Maybe you guys know better, but yeah, Blackboard is not. People don't fill out surveys on Blackboard, I guess. All right. Homework 10 is due today. There's a walkthrough release. It is written only. Yeah, please get that in on Gradescope. That would be great. Another update. I did write a script yesterday. All of your quiz grades should be up to date on Blackboard. Your midterm retakes or regrades should be up to date on Blackboard. There is a new. Oh, I haven't released it yet. I will try to release by the end of the week a like final grade estimate for you on Blackboard, which will include dropping your 2 lowest grades, dropping your 4 lowest quizzes, etc. Participation grade. Yeah, so it'll try to include everything except the final. So basically, if you do as well on the final as your current grade, then your grade will stay the same. If you do better, your grade will go up. If you do worse, your grade will go down. If you have any questions, then email me. Homework corrections, I have not gotten to, so those are not up to date yet, but I will try to get that soon. Yeah. Your homework 10 is already graded on Blackboard with an actual grade. Oh, with a 0. Oh, No. That's probably not graded yet. No, homework 10 is not graded yet because it hasn't been submitted. Sorry, I'll try to fix that on Blackboard. I guess my script might have a few bugs. I didn't consider the edge case where we had an assignment that hadn't been completed yet, I think. Okay. Yeah, no, not everybody in the class got a 0. So homework 10 is not graded yet. She's going to grade it. That's probably going to go in later. Homework corrections have not been graded yet. So, but I'll try to get that by the end of this week, I hope, or basically the end of today, or maybe over the weekend. But everything else should be up to date. If you do retake your quizzes, I will be running my script frequently to try to make sure everything stays up to date. But just as soon as you retake it, it should reflect on Blackboard pretty quickly. Cool. Any questions on the homework 10? How are you guys? Did you guys finish it? Submit it already? I know I say it. Yeah. I don't even know why I ask you guys. I feel like you guys just get everything done pretty quickly. All right. So today's lecture is going to be, again, a little bit more high level, a little bit more philosophical. We're going to talk about a very important question in computer science known as P versus NP. Okay. Has anybody heard of this before? No? Does anybody watch like The Simpsons or Futurama? A little bit? Never heard of like P, does P equal NP? Any no, okay, all right. Well, I thought it might be funny, but it does come up in popular culture quite a bit. So actually there's an entire episode in Futurama about this whole like P versus NP question. And then I think this is an episode from The Simpsons. If you notice here in the background, there's a little thing that says P equals NP. Okay. So after today's lecture, you guys are finally going to know what that means, I guess. So in case anybody makes a reference to it in the future. And here's something that you want to take away. If you're ever trying to solve P versus NP, so if this is ever a task that somebody asks you to do, you're going to have a really bad time. Okay. There is actually, so we're going to go into detail as to what the question actually means, but it is an unsolved problem in computer science, also in mathematics in a way. And most people think it is one of the most important unsolved problems. So important that if you do solve it, there's $1 million reward waiting for you for the Millennium Prize. Yeah, so that's another way to get rich if you can solve this problem. All right, so this is a pretty like theoretical problem, I'll say. Like it does not actually like, we are moving forward with the world. So this is what I'll say. The world is moving forward, assuming that P does not equal NP. And again, you guys will get a sense of what that means in a little bit. So it doesn't really have any practical implications from that point of view, but it is very important to the computer science like theory for like algorithms. And sort of like understanding this question can help us understand like what are the limitations of computation? Like, are there things that we cannot solve? Like, are there things that there is no algorithm to solve, basically? Okay. Here's, for example, like a couple of questions that maybe you guys should ask yourself. So like in this class, we've always brought up problems. And for every problem I've introduced to you, there has been an algorithm that solves it. And then I tell you guys the algorithm, you guys code it up, you understand it. And then I ask you, how fast is it? You figure out the running time, right? So there is an interesting question to be asked, for example. There are certain problems where the algorithms that we do have are not very fast. And I guess the question to ask is, have we just not like, is there a faster algorithm and are we just not smart enough to find it? Or is there not a faster algorithm? Like it's actually impossible, right? From a like mathematical, like from a physical point of view, okay? And like I said, this is literally $1 million question. It's called the Millennium Prize. There's actually 10 problems. 3 of them have been solved, or 2 of them have already been solved. Somebody got $1 million. There's 10 of them in total. This is number 1, I believe. If you solve it, you get $1 million. It's like done deal. And by solve it, that means like your peers have to agree with you that you solved it, right? You can't, you know, obviously, yeah. All right, so let's actually talk about what P versus NP means. So intuitively, what this means is that the question that it's asking is like, are problems that are easy to check also easy to solve? Okay, so P here actually represents a class of problems. It represents all problems for which there is a polynomial time algorithm to solve. Okay. NP, which does not stand for not P, it actually stands for non-deterministic polynomial time. It represents the class of problems. So all problems in the universe, in the world that you can think of, for which you can check that the answer is valid in polynomial time. Okay, here's a couple of examples, or well, I guess let's do a little bit of history. I'm going to go over some examples later in the lecture slide. But any questions on P versus NP? So what is P? What is NP? What do they represent? Yeah, right. So P represents, so the question P equals NP is asking, are all problems that are easy to solve, are all problems that have a polynomial time algorithm, for example, shortest path, sorting has a polynomial time algorithm, are all problems that have a polynomial time algorithm, is that the same set as the problems for which, when given a solution, you can check that it is the right solution? in polynomial time. Okay. And we'll go through some examples in a little bit, but that is what the question is asking. And here's a little bit of history. Like you should, like your intuition should tell you like the answer is no, right? And that is what the vast majority of computer scientists believe, that these problems are not the same. There are certain problems that to solve them is much harder than checking if you found the right solution. Okay, so for example, I guess like some of these, so before 1965, here's a set of problems that were considered to be very slow. So we did not have a good way to solve them. So for example, sorting, we've always had a fast way to sort. O of n squared is the worst case, n log n is like pretty good for merge sort, right? Greatest common divisor, there's an algorithm by Euclid that runs in linear time to find the greatest common divisor of two numbers. So those are considered fast problems. Before 1965, there's the problem of factoring. So given a number, can you find the factors that correspond to that number? Okay, that's what the problem says. Before 1965, we did not have a fast algorithm to solve that. So our best algorithm for figuring out if a number is factorable, or like to find the factors, is to try, like starting with 1, divide this number, like start with 1 divided by, or start with 2 divided by 2. If it divides by 2 evenly, then 2 is a factor. Divided by 3. If it divides by 3, then 3 is a factor. Divided by 4. If it divides by 4, then 4 is a factor. Okay. So basically, it's like iterating through all the numbers up to n, try each one, which is basically try everything. There's also a very common problem known as the traveling salesman problem. So this is a problem, for example, for UPS. So the traveling salesman is you have several locations that you want to visit. Okay. And each location is a certain distance from you. Your goal is to visit all the locations in the shortest amount of time. That is the problem. Like, can you give me a sequence of locations to visit that is the shortest, that will minimize the amount of time I spend trying to visit all the locations? The best known algorithm for traveling salesmen, even today, is you need to try all possible ways of visiting the locations. For each way, you need to calculate how long it's going to take you, and then I can tell you which one's the fastest. But if you have n locations, what is all possible orders of visiting them? How many are there? You have n locations, and you're trying to figure out how many ways can I order n items. Yeah. It's a little bit faster, like smaller than that, actually. It's n factorial. Yeah. So n factorial tells you how many ways can I order n items, right? The fastest known algorithm for traveling salesman is basically big omega of n factorial. Like it's a minimum n factorial. Now, here's a couple of other ones. I'm not going into too much detail into this one, but this, before 1965, determining if a number was prime. So I give you a random number, and you want to know if it's prime, was considered to be just as hard as factoring. Because basically, the algorithm that we had is given a number, factor it. If there's only 2 factors, it's prime, right? We're not going to cover the discrete Fourier transform. But basically, over time, what happened is, I think in 1965, Cooley and Tukey actually discovered a polynomial time algorithm for this problem called the discrete Fourier transform, which has to do with like wave analysis and stuff. You don't need to know it. So it moved from being slow to being fast. In 2002, we actually discovered something called the AKS primality test, which is a polynomial time algorithm to determine if a number is prime. So these are 2 examples of problems that so from 1965 to 2002, this problem, we did not know if there was a faster algorithm. People tried for 30-something years to find a faster algorithm, and they never succeeded. So we thought it was impossible until 2002 when somebody actually came up with it. So we just weren't smart enough to like figure it out, right? So the question remains, like, so basically what P versus NP is asking is, today for these problems, we don't have a faster algorithm. P versus NP is asking, are we just not smart enough and we're going to find one in the future? Or are there problems that cannot be solved faster than polynomial time? Okay. Or like polynomial time or faster. Cool. Something like super interesting as well to like wrap some of this discussion about P versus NP up is that there's something called the Cook-Lovin theorem. So there's a lot of like computer science, like theoretical side of things. Okay, like we're just touching the surface. We're not going to explain why this works and how it works. But what this problem found is they actually have found a set of problems that are considered NP complete. Okay. So there's this class of problems called NP complete. And what that means is that every single problem in NP, all NP problems. So basically, all the problems that we know are hard to solve are equal to the NP complete problems. So what they did is they actually found one problem that if you solve that one problem, you have solved traveling salesman, you have solved factoring. So you actually don't have to solve these problems independently. What they did is they got really far. They found a way, and they're called NP complete, the problems that are NP complete. They found a set of problems that if you solve any one of them, you have solved all of the hard problems that we have in computer science. Okay, so we're not going to go into too much detail as to like how that works, but if you want to solve P versus NP, there are a set of problems that if you can solve any one of them, then you have solved all of the NP problems. Okay, and one of them is actually, I believe one of them is actually factoring, but okay. So here's like a visualization. So like I said before, P and NP are sets of problems that require an algorithm. We know that P is a subset of NP. So we know that all problems that you can solve in polynomial time, you can verify in polynomial time. Why? Yeah. A little bit. Yeah, let's say this. Let's say we have a graph. We have a giant graph, okay? And you're trying to figure out the shortest path from one node to another, okay? That's the problem, okay? I come to you and I say, this is the shortest path, okay? So I give you a path and I tell you, this is the shortest path from U to V. How would you check if I was right or wrong? Yeah. Can you be a little bit more precise? Like you want to check quickly, so you don't want to try all possible paths, but it's not like it's not a trick question. If you're thinking it's like a really obvious answer, that's probably the answer. Yeah. Right. So here's the problem. So I'm telling you, I come to you and I tell you there's a node U and there's a node V, and there's like a ton of other nodes around them, right? And I say, okay, this path here, like if you take this path, right? I tell you this is the shortest one, and it has cost 25. How would you check whether I was right or wrong? Not quite. Yeah, David. So I'm not giving you a program. I'm just giving you the shortest path. But you would run. Right. Perfect. Right. So because there's a polynomial time algorithm to solve the shortest path problem, what you would do to check me is you would just take the graph, run Dijkstra, run BFS, find the actual shortest path, and then compare it to mine. right? So that's why every problem that you can solve in polynomial time, you can also check to see if the answer is right in polynomial time, because you can just solve it, and you can just solve it yourself, right? Okay. Cool. So here's a couple of other problems that are included. So these are all problems that we've actually covered. These are all included in P. So these are all polynomial time solvable. So like I mentioned, finding the greatest common divisor, linear programming is polynomial time. Most of the algorithms we covered in class were polynomial time. If you guys remember, we didn't really want to, I think except for the dynamic programming algorithms, most of them are polynomial time. But it has taken, like I mentioned, for determining if a number is prime, we didn't know that we could do it in polynomial time until 2002. Everybody thought it was a very hard problem, right? Now, let's try to understand the set NP a little bit more. So this stands for non-deterministic polynomial time, okay? So this is the set of problems, decision problems, for which there exists a polynomial time algorithm to check if a solution is correct. So here are a couple of examples, but I think the one we can talk about is Sudoku, okay? So we do not have a polynomial time algorithm to solve Sudoku. So if I give you a grid, is everyone familiar with how Sudoku works? Has anybody played it before a little bit? Does anybody want to explain what the rules are? Yeah, go ahead. Yeah. Okay. Yeah. Yeah. So that's exactly, it's a Sudoku. Is the rule is that for every row and for every column, you can only have the numbers 1 through 9 once, right? And then also for every square, for every 3 by 3 square, the numbers 1 through 9 occur once. Okay. Now, has anybody solved, like, have you guys played Sudoku? Okay. No. Yeah. Sometimes. Have you ever tried to come up with an algorithm to solve Sudoku? Okay. Here's what I'll tell you. All known algorithms to solve Sudoku are exponential. We do not have a polynomial time. So if we define n to be the size of the grid, so let's say it's n by n. So this is going to be like a bigger Sudoku than our normal, but the rules are still the same. We do not have basically the fastest algorithms that we have ever come up with for Sudoku are try all valid, like just try the numbers like 1 by 1 and then keep checking if it works. And basically that's it. Like it's even worse than whatever you're doing probably in your head, right? But if I gave you a completed Sudoku grid, could you check if the solution was valid in polynomial time? How would you check in polynomial time? What is the algorithm you would use to check? And it has to be O of n to the k, where k is some number. And again, it's not a trick question. Like the algorithm you're thinking of is polynomial time probably. I say. Yeah. So you would start with, hey, I need to make sure that all the rows have the numbers 1 through 9. So let me just look at every row. Let me clear. Look at every row. Oh my. Look at each row. How long is it going to take me to check each row, like to check one row? Huh? Yeah, n, because you look at each number and you can, for example, you can put it into a hash set and you can say like, do I have all the unique 1 through 9 numbers, right? So it takes you O of n time for each row. So in total, checking the rows is going to take you O of n squared because you have n rows, so you're going to check n values. Okay, so that's O of n squared. Should be pretty obvious to you guys that checking the columns is the exact same process, except you're going column by column. So that's also O of n squared. And then you check each, 3 by 3 grid. that's also O of n squared because you look at each number once. So checking if you're like, if one of you comes to me with a Sudoku puzzle and you say, here's the answer to it, here's the solution. Checking it is very easy in a way, right? Checking to make sure you're right. All right. So that is an example of a problem that is an NP. Okay. Now, you can imagine there are also even harder problems. We're not going to really talk about this, but you can imagine there are problems that even checking if the solution is right, we don't know how to do it quickly. Okay. So we're not going to talk about this, but there are other problems where we don't even know how to check if the solution is the best solution. Okay. All right, so let's go through these, and I want you guys to tell me if, so the first question is whether these problems are in NP. So that means, can you check if a solution is right in polynomial time? And then if they're in P, which means, can you come up with a solution in polynomial time? So sorting a list, is it in NP? Yes, right? How do you check if a list is sorted? You iterate over it. So it's going to be O of n time to check. Okay. Is it in P? Yes. How do you sort it? You use merge sort. Okay, great. Multiplying two numbers. How do you check that I multiplied them correctly? You multiply them yourself and you check to see if the answer makes sense, right? So yes, this is both in P and NP. So all of these, so this is in P, this is in P. Okay. Given a set of vertices and edges, is the graph connected? Is this an NP? Is this in P? P, Isaiah says maybe, yes. It is an NP, okay, so there's definitely one for, there's a vote for NP. How would you check? So I give you a graph and I tell you, yes, it's connected. And here are the edges that make it connected. How would you check? Yeah. Yeah. Now, if I just give you a graph and I ask you, is it connected or not? How would you guys figure it out? Yeah, Lester? Yes. So Leander's right. You can just run DFS from any node. DFS will find all the connected components, right? If you ever pop out of DFS and you have to restart it, then that means your graph is not connected. And the running time of DFS is polynomial, right? So this is in NP. It is also in P. Okay. Rubik's cube. This one's a little bit harder. Does anybody do Rubik's cubes in class? Any competitive Rubik's cubers? No. Okay, so I'll give you guys this one. Well, okay. Well, first of all, how would you check if a Rubik's cube is solved? Like if do you guys know how Rubik's cube works? So they have like different colors on each side, and then they start random, and then you have to like turn, and then once you get all of the faces to be the same, like each face is the same color, then you're done. Okay. Is checking if a Rubik's cube is solved can you do that in polynomial time? Yes, because you just check the faces to see if they're all the same color, right? Okay. Is solving a Rubik's cube, can you do that in polynomial time? Yeah. You wouldn't necessarily know. I wouldn't necessarily know this, but yes, it does turn out there is an algorithm that is actually very simple that takes a polynomial number. It is polynomial time to solve the Rubik's cube, which basically is like if it looks like this, then you have to turn this one this way or something. So this one is also an NP. All right. So let's talk about chess. Everybody knows how to play chess, right? This is interesting. If I gave you, if let's say we're playing chess, and I tell you moving this knight to this position is the best possible move that you can make. How would you check if that's true? Depends on how many moves it takes to get to checkmate. Okay. So in general, think of the worst case. So we're just starting our game, and I tell you, oh, the best move is to move this pawn forward 2 spots. Yeah. Yeah. So it actually turns out that this is an example of a problem where we don't even know how to check if your answer is right. The only way we know how to check is to try to find the optimal move. And the only way we know to find the optimal move is if you get lucky and you're very close to the end, you can just try all of them and see which one's the best. If you're not very close to the end of the game, then trying all of them means that you're going to wait until the universe dies, and then you'll know what the answer is. I think we had a problem like this one, either in the midterm or homework assignment. Subset sum, actually maybe a little bit different. So the problem is there a subset of some set? Is there a subset of some set of numbers that sums to a specific value? Okay. Is that in NP? If I give you the set and I also give you the subset, can you check in polynomial time that subset sums to the value? Yes, you just add up the numbers in the subset. It turns out that this is not in polynomial. You cannot solve it in polynomial time. The best known algorithm is to try every subset of numbers, which is 2 to the n. How many subsets are there? If there's n numbers, there's 2 to the n subsets. So at minimum, you're going to do 2 to the n. So now you guys hopefully you have a better understanding of P versus NP. We talked about a few example problems that are in each class. There's a lot more. Okay. We actually already talked about Sudoku, so let's quickly go through this. This is another problem that's in NP, but not in P, for example. Is there an ascending subsequence of length at least 7? So do you guys remember what a subsequence is? Yes, it's just a sequence from the array or the string that's still in order, right? So all it's asking is, like, given an arbitrary array, is there a subsequence that is only increasing that has length exactly 7? So is this an NP? If I gave you a subsequence and an array, could you check that this is the right answer? Yes, you look at the subsequence, you check to make sure it's of length 7, and then you check that it's increasing, right? Again, it turns out that to find the solution, though, the best known algorithm is try all possible subsequences and check each one. Okay? This is similar to the traveling salesman problem. So this is called, is there a simple path that goes through every node exactly once? So given a graph, a simple path is a path that has no cycles, okay? And the question is there a path that hits every node exactly once that I can traverse in one direction? So this is not an MST. So an MST is just a tree that spans the graph. A simple path has to start, you can imagine it has to start somewhere, and I have to be able to get to 2, then to 3, then to 4, then to 5, then to 6. I have to be able to walk the path. I cannot just jump to another node. I have to walk it. So this problem is an NP. Why? If I gave you a graph and I said, this is a simple path, how would you check to make sure I was right? Yeah. Take it out of the graph. Oh, take the nodes that are out of the graph. Yeah. So in a way, like try to like follow the path I gave you. Like try to take the path I gave you. Every node that you reach, take it out of the graph. And then if you have nodes left over, that means the path is not simple because it didn't touch everything, right? This problem is not in P. We do not know a way to solve this quickly. Again, other than like try all possible paths and then see which one hits all the nodes. Okay, so there are a lot more problems. So if you guys are interested in this, this is what is called, I would say, computational theory in computer science. So it is thinking about what are the problems that we can actually solve? What are the problems that we can solve quickly? And thinking about them as a set of problems. So there's a lot of them here. So we actually talked like maximum cut. So we talked in class about minimum ST cut. There's an equivalent problem called the maximum cut problem, which is like find a way to split the vertices such that the cut is the biggest possible. That is actually, we don't have a polynomial time algorithm for that. This problem is actually considered to be like really hard. Okay. And then there's a lot of other ones that come up. Cool. So the last thing, I'm actually going to skip this part on reductions. So I want to get to the end. All right, let me see. Let me see what part I want to get to. Okay. Okay, let's do it. That's fine. Okay. So we're going to introduce this concept called a reduction. So a reduction is a polynomial time algorithm that converts a solution of one problem to a solution of another problem. You guys actually already did this. So for example, when we were talking about max flow, I would give you guys a problem statement that talked about, you know, employees and offices and like how many employees fit in an office and where the employees want to go. And you guys reduced it to a max flow problem by saying, oh, for each employee, I can create a node. For each node, I can like connect it this way. And then when I connect it, I can set the capacities to be, you know, this value. And then I can just run the max flow algorithm and that'll give me an answer. Okay. So you can imagine that, and that is a polynomial time. So a reduction is a polynomial time algorithm that converts a solution of one problem to a solution of another. We're going to talk about these three problems. So this is just to give you a taste of the Cook-Lovin theorem. So if you guys remember, I told you like, hey, they figured out that there's like these set of problems that if you solve this problem, you solve everything else, right? So for example, these are three different problems that are all the same. Okay. So the first problem is called the independent set problem, which is given a graph, I want you to give me the set of nodes the maximum set of nodes that do not connect to each other. So pick the nodes in a graph such that they don't form, there is no connection between the nodes you picked. And pick as many of them as possible, right? So yeah, the vertex cover problem is pick the nodes in a graph such that they see all the edges. So this is actually the all-seeing problem that you guys saw in one of your homework assignments. And then the click problem is find a subset of the graph that is find the biggest subset of the graph that is fully connected to each other. Okay. Okay, so let's try to do a couple of reductions here. So this is the original. So we have an original graph. How would you, so independent set, for example, this is the maximal independent set because this is the set of four nodes that do not connect to each other. Okay. If you had a way to solve the independent set problem, how would you solve the vertex cover problem, which is the set of vertices that see all the edges? And maybe, hopefully the picture gives you a hint. Yeah. Yeah, so so if I had a way to solve the independent set problem and I'm given a graph, but I want to solve the vertex cover problem. So I know how to get all of the nodes that when I pick them, they're completely independent from each other, right? So for example, this blue node does not connect to another blue node, right? But what I want to solve is I want to find all of the nodes that when I pick them, they actually cover all of the edges. So they see all the edges, okay? So does this picture give you a hint of like how you might solve this problem by solving this one? Yeah. Yes. And that is the reduction, right? So if you had a solution for independent set and I gave you the vertex cover problem, you could say run independent set on it. That'll give you these blue nodes. All the nodes that weren't blue, those are the ones that are in the vertex cover. Okay. Okay, we're a little bit short on time, so I'm going to skip the next one. But it's a similar idea. Hopefully you guys can look at the picture a bit. We're going to skip this one because it's more complicated. And we're going to jump back to like philosophy. So I thought this was funny. So there's a couple of things. Yeah, you guys can read it. Can't find an efficient algorithm, but neither can all these other famous people. So again, it's important to know that there are certain problems that we don't have efficient solutions for. If you ever recognize it while you're working, like there are going to be non-technical people that ask you to solve certain problems. Sometimes those problems are not solvable. So, you want to be able, like if you can reduce it to a known unsolvable problem, then you can just tell them, well, this is, people have been trying for the last 40 years. We're not going to do this, right? Here's another like more direct reduction. So let's try it in class. So again, given an undirected graph G, a matching is a set of edges so that no two edges share an endpoint. Okay, so we talked about matchings in bipartite graphs before. A maximum matching is a matching with the largest number of edges. Okay, does that make sense? So a matching is like, this is my graph. A matching is take some of the edges such that none of the nodes are connected to each other. Okay. A maximum matching is take as many of the edges as possible, right? So this is a matching, this is a maximum matching. Because it turns out you can actually take 3 edges without connecting any of the nodes. Where this one you only took 2. Okay. Let's skip that part. Here's an example problem I might ask you. So this is called the domino tiling problem. And I did just introduce maximum matching, so hopefully that gives you a hint. The domino tiling problem is given a board where there are certain spaces marked as black, which means you cannot put a domino there. And there are certain spaces marked as white, which means you can place a domino there. What is the maximum number of dominoes that you can place? Where a domino takes up 2 spots, either horizontally or vertically. Any ideas how to solve this problem? Yeah. That is a great approximation algorithm. And that is probably, so it turns out maximum matching is NP complete. So there is no fast way to do it. But the algorithm you suggested will not always give you the right answer, but it'll be off by at most a factor of 2. So it's actually pretty, like in practice, it might be very good. Yeah. And that's actually probably what you would use in the real world because the actual algorithm is exponential. So it takes too long. But if somebody came to you and asked you this and say, hey, I want to solve it exactly, how would you convince them that it's too difficult to solve exactly? So they already know. So there are research papers that say the maximum matching is NP complete. So there is no known polynomial time algorithm to solve maximum matching. Why does that mean there is no polynomial time algorithm to solve domino tiling? How can this problem become a maximum matching problem? Yeah. Sorry, could you speak up a little bit? So like insert it and yeah. Very close. I think you're actually you might be overthinking it a little bit. Yes, Serena.
So you could represent the Domino spaces as like the graph would be like all the white space. So each node would be a white space basically. And then the matching sets would be like one graph.
I think you're off at the end, but that is the idea. I think you might have overthought it a little bit, but I'm not sure. So that's exactly what you do. So for every blank space, you represent it as a node, okay, in your graph. If there's two white spaces that are adjacent to each other, you connect them with an edge, okay? Now, finding the maximum matching in this graph is the same as finding where to put the dominoes, okay? Because so this is the graph, this is the maximum matching. That tells you that you should have a domino connecting the vertices you matched, okay? Oh, I had a slide for that, that's great. Okay, so that is what we consider a reduction. Let's really quickly, like I'm gonna wrap up just a few minutes. The last things are not super important, but they're kind of cool. So in general, 83% of computer scientists believe that P does not equal NP, okay? The main reason that they believe this is that it has been extremely difficult to prove whether P equals NP or not. So there is no proof. So we don't know for sure it's not equal, but nobody has shown it's equal, no one's shown it's not equal. Most people believe it's not equal. And that's because for the past 43 years, people have been trying to prove this and nobody has figured out how. The other part is that if P does equal NP, that means that every problem that's easy to check, like that you can check in polynomial time, is also easy to solve. And that actually means that so we use RSA encryption for our communication. This relies on P not being equal to NP. If they're equal, that means you can crack RSA encryption in polynomial time, okay? Yeah, here's another way to put it. This is from the philosopher Scott Arison at MIT. He said, if P equals NP, the world would be a profoundly different place. There would be no special value in creative leaps, no fundamental gap between solving a problem and recognizing the solution once it's found. Everyone who could appreciate a symphony would be Mozart. Everyone who could follow a step-by-step argument would be Gauss. Okay, so if they are equal, that means that every problem that you can check quickly, you can also solve quickly. So the majority of computer scientists believe they're not equal, but we've never proved it. And the vast majority of our encryption relies on this fact. But it's okay. So we'll wrap up the class there. That's it. That's the end of all the content that you actually have to cover. We're going to do review for the next 2 lectures. And I'll try to bring pizza on Monday for you guys. So if you have any dietary restrictions, shoot me an email, let me know. Otherwise, I'll probably bring like cheese, pepperoni, and maybe that's it. I don't know. I'll pick something. Cool. All right, see you guys on Zoom. Thanks for coming.